So today I want to do unitary groups in some detail. And I want to convince you that they're the mother of all groups, at least all finite groups and all so-called compact groups, kind of groups you care about, like rotations. Start easy. Let's start in one complex dimension. So U1 is a group of rotations in one complex dimension. Now, we know it's not totally trivial, this thing, because we know that Gauss or Argon or somebody figured out that the way to think of complex numbers is to plot them in a plane with real and imaginary parts. And that one complex number is really two real numbers, and convenient way is to say a point in a complex plane has a distance, we'll call it radius, and an angle with respect to the real axis. So now when we say a vector, if you write it as a complex number, it's a little bit weird because, it's just a number. But if you write it as in its polar representation, then, it makes a little bit more sense. It has a real number signifying the radius in a complex plane. And then it has a phase. And this is now a point in complex space of dimension 1 complex number. That's what U1 refers to. 1 is the dimension in a complex space. Even though when you think of it as a real thing, it's two-dimensional. One can associate length with it, which is usually called modulus, by defining a complex conjugate and then constructing of the complex conjugate and its the original number, multiplying by usual rule, we get square of the radius, so square of the length. Now, why is this called unitary group? Well, we can define a group element as a complex number of radius 1, length 1. That's what unitary means. It's a unit in radius. And it satisfies group properties. If I multiply two of these guys, their phases add up. So multiplication is addition in the phases. And if I apply it to this number here, Z, I'll get a new number in a complex plane. So it acts on this space by moving things around. And, it's a complex number, but you can think of it in this case as 2 cross 2 real matrix. It's not totally trivial. And if you think of a real matrix, that will be called special orthogonal group in 2 dimensions. So if you think of it in this way, then it's a 2-dimensional thing, not trivial. And the length is an invariant of this transformation. Because if I look at this number, take its complex conjugate, multiply it by itself, there'll be r I theta r plus I theta. Only relative sign is important. And that's length square, but that's the same as the original length square. So unitary group U1 rotates things in a complex plane while preserving the length. And the crucial thing is that it's a transformation of all possible transformations you could do in this complex plane. It's the one that has an invariant length. That's unitary group U1. Unitary group U2. We take two complex dimensions. In other words, the space in which our vectors live has two components, Z1, Z2, and each one is a complex number, so that's an element of complex numbers twice. And now we define a Hermitian conjugate, so this is a dagger, or after the French mathematician from the French Revolution, Hermite, it's called Hermitian. And it's called conjugate because of some stupid Latin background I had. Sorry, brilliant Latin background I got indoctrinated in the fancy schools.
Can I ask a question?
Yeah.
So, a lot of times when you're thinking of the complex plane, like C1, you can think of that as being analogous to R2. Would it make any sense to go from C2 to R4, or does that just get like complicated?
Yeah, but we don't do it because our visualizations fail us. So nobody tries to draw this because it's a four-dimensional space, and what are you going to do with it? So by the moment we move to two complex dimensions, we tend to keep it just as algebra and not draw pictures. But you're right, it is four-dimensional space. But a very special one because it's built of little two-dimensional blocks, which are these complex numbers. But anyway, you can define a Hermitian conjugate where you transpose the vector, so you make a column into a row, and every element of it you take complex conjugate. When you do this, you can define a dot product between two vectors in a complex space. And there are various notations. So in physics, quantum physics, people often use Dirac notation. So this is called Dirac bra, and then ket, just a way of writing a bracket, putting things in a bracket. If you don't like that notation, you can use usual vector notation. So you take a vector x with two complex components, you transpose it a complex conjugate, and then you write a dot. The other vector, which means you write it as x1, first component complex conjugate, second component complex conjugate. So it's a row, and you multiply it by a column, y1, y2, two complex numbers, and you get complex conjugate of first times that, complex conjugate of the second times that. So that's how you define product in this space in two dimensions. And now you can define length by Pythagoras theorem. But because this is a special case of, many ways of defining lengths, this mathematicians call norm. And norm is just a dot product of vector with itself. You can write it as vector z absolute value squared. The reason why that makes sense is that if you take it dotted with itself like that, you get the first guy, complex conjugate time itself, second guy, complex conjugate time itself, which is R1 square plus R2 square. And this is really the correct definition of distance in this 4 dimensions, because, this R1 and R2 squares were already 2-dimensional distances, and you add them up and you get a length of the vector in 4 dimensions. Now, here the norm or length plays a non-trivial, an essential role in defining what you mean by unitary group, because you can write all kinds of matrices which are 2 by 2 matrices that multiply to complex number and give you 2 complex numbers. But you want them to preserve the length. You define them in such a way that length is invariant. And that's the essence of group theory. Group theory tries to implement mathematically what you mean by a symmetry. And in particular, if you have a vector, you like to preserve its length, and this is a correct generalization of complex vector definition of its length. So unitary group will really be only those complex matrices that, when applied to a vector, preserve its length. So the element of any group, if it's a 2-dimensional matrix representation, it'll have 4 elements. It's just a matrix. And because you're acting on complex numbers, these 4 numbers are 4 complex numbers. And conventionally, one writes it in the following way. This number 4 we write as a product of 2 times 2, which reminds us that what this matrix does is it works on 2-dimensional vectors, multiplies it, and gets a new 2-dimensional vector. So, 2 is reminding you that you go from 2 dimensions into 2 dimensions by a matrix multiplication by 2 by 2 matrix. Now, if these are complex numbers, obviously there is closure, meaning that if I multiply 2 of these matrices, I multiply it out, I get another matrix, call it U3, and that's just full of complex numbers, so no problem there. It has this property that a multiplication, a group multiplication, because it's a matrix representation, just matrix, no problem. And that if you multiply 2 matrices, you get something in the same definition of the group, in this case, complex numbers. It has identity. So there is a special element whose matrix representation is 1, 0, 0, 1. So that's, a particular matrix in which 2 components are 0 and the 2 other ones are real and equal, size 1. But then to have a group, you need an inverse. This is now abstract definition of the group. And what is this inverse? That's fixed by demanding that the length is invariant. In other words, if I take a column vector of length 2, this one, and multiply it by its transpose complex conjugate, or the Hermitian conjugate, I can write this as original vector multiplied 2 by 2 matrix. It has 2 components. We'll lay them out horizontally. and we take a complex conjugate. And then I dotted with the original vector multiplied by matrix U. This is again column of height 2. And I computed, and now the only thing, if you don't know it, you have to write it as sums and check it, is that whenever you have this form, you can write this as Hermitian conjugate of the matrix multiplying the transpose. So that's how you can rewrite this thing. That's that part. Times the matrix U multiplying the column on these. Now, what's this Hermitian conjugate of a matrix? We know we have defined it for the vectors. You take all the components and you first transpose them. So this becomes U21, U12 compared to this matrix. On diagonal, they stay them put. I take complex conjugate of everybody. That's a Hermitian conjugate. And now this should be true for any Z, which means the matrices have to satisfy something because they should be independent of Z. And what they have to satisfy is that when you multiply two of these guys, you get identity. And if you get identity here, then of course this norm equals, the norm in terms of original guys, we have Z prime square equals Z square. And it's this property that is called unitary. Matrix that satisfies this property is called unitary. And what's special about that matrix is that now I know what the inverse is. Inverse of U. So, inverse operation minus 1, which is in matrix algebra, that's inverse of the matrix, in a matrix representation. Well, that's just original matrix transpose and complex conjugated. So now you have inverse, and associativity is trivial because matrices have associative multiplication. So that indeed, the complex matrices which satisfy the property the Hermitian conjugate is inverse, indeed close a group which has a property that it doesn't change lengths. Now in quantum mechanics you run into this because you have complex wave functions, but you interpret their norm wave function multiplied by its complex conjugate summed or integrated. You interpret this as a probability, and that should be an invariant prediction of quantum mechanics. So the only transformations of wave functions that are allowed have to be unitary. In electromagnetism, you have waves and you want to measure the power, which has to do with the strength of electric and magnetic fields square. And that's why you get unitary things there, but also you get them because you're in Fourier modes and they're complex numbers and blah, blah, blah. So it's a very natural thing. So now that you've figured out what unitary group is in 2 dimension, you immediately write it in any dimension. That's called unitary group UN. And what it has is it has a notion of a vector or a state or something, Z, and now it's in n complex dimensions. Now that's the state that unitary group acts on. It acts on d-dimensional complex space. what's the group itself? We have the first property, you take a d-dimensional complex matrix, you multiply it, and you associate this with some abstract group operation G1, G2, you multiply them, and you get a complex matrix. And that one you associate, because it's supposed to be representation, with the group elements applied in this sequence. So by construction, it has closure. Now, it always has an identity element, which is a diagonal matrix in d dimensions. So there is always identity. Now, it's associative because if I take U of G1, U of G2, I multiply them, and I multiply them by the third unitary operation. That's the same as U in the other order, so it's associative. And, it has this incredibly simple inverse. I mean, you just take the matrix, and to get the inverse element, you just transpose the matrix and complex conjugate elements. So, there's no work in getting inverse. It's a simple thing. Now, why is that called unitary? If you take a determinant of Hermitian conjugate of a matrix multiplied by the matrix, that's a unity, and determinant of unity is 1. But by matrix multiplication rule for determinant, that's the same as computing determinant of U. Now, you can easily check the transpose of the function and matrix and matrix are the same, but there's also complex conjugate times determinant U. These are just numbers, and it says a number times its complex conjugate is 1. So this number cannot be anything else than a complex number whose modulus or length is 1 and is a pure phase. In other words, this general is the thing we're familiar from finite groups. In finite groups, it had to be nth root of unity. Now it just has to be a complex number sitting on a unit circle in a complex plane. So that's why it's called unitary, because it has all the elements have unit length. Their volume is a unit volume. They don't change volumes like matrices usually do. And then there is a obvious specialization, so it's called special. Unitary group SUN, and it's a subgroup of unitary group with additional restriction, the determinant of the matrix equals 1 and not the phase. And that turns out to be very easy to implement in practice. So in practice, and for many other reasons, people tend to really study special unitary groups. You see them all over the place. You have reduced this overall phase, but sometimes you study a unitary group with the phase. So that's a unitary and special unitary group in n dimensions. And, why do we care? I mean, complex numbers are natural. as opposed to the real numbers. Well, we found out that while we were doing finite groups, we didn't want to, but we got complex numbers because it turned out that to diagonalize cyclic rotations, we had to do it by complex phases. So even though we started with perfectly sensible matrices full of 0, 1s, etc., we ended up with complex things. So we cannot avoid complex stuff, and it turns out it's more than cannot avoid it. Turns out that UN is the mother of all groups that we care about. I have to be a little more precise. One thing that's very surprising that I couldn't do justice in a week of studying finite groups was that UN, every finite group is a subgroup of UN. You know it for Fourier because Fourier was unitary stuff that diagonalize cyclic rotations. I kind of hinted at it that generalizes. So you go from, you go from a group multiplication table for cyclic thing to class multiplication table in terms of character, where characters are unitary. But I couldn't really derive all the necessary things, though it's done beautifully in many books. So very counterintuitively, you start with something that, for example, permutes 6 billiard balls, label 1 to 6, but its intrinsic coordinates are complex, and the correct way to think about it is, how you permute them is by unitary matrices. Now, it turns out we know that on a circle we can go to the limit. So we learned it for things like, 3 things on a circle. So that was called cyclic group with 3 elements, and the elements did things like that. They sent everybody by 1 notch around. But then we also learned that has a nice continuous limit when I take infinitely many elements, where a group element sends me from here to there by any angle, not just rational angle, theta. And that is the group that we just looked at, U1. And if we think of the plane, it's called special orthogonal group in 2 dimensions. So that's an example of a compact group. The word compact means that the values that the parameter theta can take are compact from 0 to 2 pi, as opposed to if we were moving on a line, then we would have, something that goes from minus to plus infinity as a parameter. There'll be a non-compact group. Those are also interesting, but, let's do compact first. So this is very simple. It was simple because these were abelian groups, so they were easy to do. Didn't have to worry about ordering of the generators. Then the first example of a non-abelian group was you took triangle or 3 scattering disks in a plane or 3 billiard balls of different colors. It was different labels, any way you want to think about it. And you allow them not only to rotate, but to flip. And that turned out to be a non-commuting, so non-abelian operations. That's called dihedral group 3. And then, it goes on. You can, for example, take 4 billiard balls with different labels, and then you can interchange them any way you want. So, for example, you can interchange these 2 and these 2, and all of those things are called symmetric group acting on 4 elements. This goes on, There are lots of finite groups. They're all classified now. There is the monster, which is a humongous group. And for all of them, they all have unitary representations. Now, the thing that we'll do in the course, but it's just the beginning of the whole story, is we'll start moving on, not on a circle, but on a sphere, planet Earth, if you wish. In that case, we are moving on the surface of a sphere, and we need more parameters to tell us where we are. It's not enough to just go around the equator. We need also the latitude, and we need to know how we are already. So we need actually 3 parameters, and that group in human intuition we call special orthogonal group in 3 dimensions. Thing that preserves length in 3 dimensions, but turns out to be isomorphic, just like here. We didn't ask for complex groups, but they happen to be same as SO2. That turns out to be isomorphic to the U2 group that we discussed. Complex group is 2 complex elements. And then, this goes on in physics. In physics, it's used to excess. So, for example, after a few centuries and lots of pondering, it turns out that particles themselves have so-called internal symmetries, not just spatial one. And those symmetries have to be classified. And you end up with a standard model of particle physics, which tells you how quarks and leptons build everything that we know currently. And, this goes on. We do not know where it'll stop. In the last few decades, there was something called superstrings, which is marching along this path, and, other obscure names. But it's a very dominant way of thinking. Compact groups are immensely important. And every time you have a compact group, it's a subgroup of a unitary group. So it's handy to understand unitary groups. And, these things are examples of the real space. Obviously, you have a complex space. If you put all imaginary components to 0, you have a real space. And equally obviously, that means that if I have a group UN, the rotation group will always be subgroup. So the UN will be matrices with complex conjugate whose Hermitian conjugate is inverse, and rotation group will be subset of those matrices with real entries in them, whose transpose, because Hermitian conjugation is trivial, it's real numbers, whose transpose is inverse. So that's why no matter what you do, you end up learning about unitary groups. The big problem with unitary groups, continuous groups, is that they're parameterized not by integers, but by fractions. And not by fractions, but by real numbers. In other words, there are infinitely many unitary matrices because any matrix which has complex entries and satisfies that it's its own Hermitian, its Hermitian conjugate is inverse, it's inverse, so it's one condition on all these matrices. Every one of them is good, but I can change any numbers as I wish. So there are continuum infinity of them. So what do? And here is the basic idea that I started the course with because it's so basic. We did it the first week. Whenever you have a matrix and it acts linearly in something, we know that solutions like to be either exponentials or sines or cosines, which are oscillating exponentials. In other words, let's try writing a unitary matrix as, and this in hindsight is a good choice to put in explicit imaginary units here, as exponential of some other matrix. All I'm saying, if I had a real number, I can always write it as an exponential of another number. In other words, I can think of a number as a logarithm of another one, and that's often helps because multiplication, which is some messy process, once you go up to exponents, it becomes addition in exponent because things multiply by exponents adding, and that's a big saving. So let's decide to write matrices in this form, unitary matrices. Now, they have to satisfy the defining property of unitary matrices that if I take two of these guys and multiply them, that's the same as taking complex Hermitian conjugate of this thing. I can expand it as a series and I can do it all the terms if you don't like looking at an exponent. But basically, I must go to minus I, and this matrix must go to its Hermitian conjugate. Now, you have to convince yourself, and maybe it doesn't matter very much because I'll pretty soon show it anyhow in practice, that matrix and its Hermitian conjugate commute. Now, even if I'm wrong, the rest you prove me wrong and I'll have to censor this lecture. But, as I multiply them, I get that this matrix minus its Hermitian conjugate has to be 0 because this has to be 1 and e to the 0 equals 1. So it turns out if matrix is unitary, it's a logarithm or it's Hermitian. Hermitian means that under operation of Hermitian conjugation, matrix doesn't change. Now, these are n by n matrices. These are not just numbers. Does this make sense? Well, for U1, the group element was multiplication by a complex phase and requiring that what's upstairs, complex, it's one-dimensional transpose is trivial, so complex conjugate is that. It's just that the phase is real number, but that was so natural to it, we barely mentioned it. Of course, phase is a real number. It's angle between 0 and 2 pi. Now for U2, let's test this. Hermitian matrix says that it's something that on the diagonal, I transpose diagonal elements on Go, but I complex conjugate them, and that has to be the same number. In other words, diagonal has to have real numbers. And if I have a complex pair of the diagonal, then Hermitian conjugation says it has to be same as I transpose or take complex conjugate. In other words, here it has 1, 2 minus I, B, 1, 2. So there are 4 numbers. And this is now a big deal because there are infinitely many of these unitary matrices. But if I write them in this form, I claim that 4 numbers will be enough to specify all of these matrices. Here it wasn't obvious, but here it's explicit. Now, if you specialize for a special unitary group in 2 dimensions, then you must require the determinant of U is 1 But you prove this amazing identity that says if I take determinant of any matrix, takes its logarithm, that's the same as a trace of the logarithm of any matrix, true for any, including unitary. Now, if the terminal is 1, its logarithm is 0. But on the right-hand side, logarithm of u is this matrix times I, which doesn't matter. So we find out that the trace of h, this is IH. Has to be 0. Or as one says in the business, the matrix is traceless. Now look at this, and I can write out explicitly very convenient formula. It says these two guys have to add up to 0, so this one is negative of this one. So I can write this as h11 times 1 minus 1, 0, 0. So that's this part. Then I have to add up to it something that's same on the off diagonal. That's this part. And then I have to add up another real number, b12. But now it multiplies I here minus I here. And I look at this, I realize, I can write the SUN logarithm of my unitary matrix, the thing in exponent. I can write it as H sum of some numbers. I'll call them angles, but doesn't matter. I'll have to, because there's an I in front, there'll be some periodicity in this business. And then I'll call this kind of matrices. Now, n by n matrices, they'll be Hermitian, by construction Hermitian.
Are those the Pauli?
What do you say?
Are those the Pauli matrices?
And very educated people recognize those as Pauli matrices. But that's where they come in SU2. They have a name. They're called Pauli. You're right. But this carries to any unitary group of any dimension. And what's the big deal? If you do this, even though you have infinitely many group elements, you can write a table like we did for finite groups that specify what it is. There's a finite number of these guys, and they have a name. They're called generators. So for any finite unitary group, you can rewrite any group element as a sum of, I equals 1, and I'll put here n. For example, there were 4 parameters for unitary group, but actually there is one trace condition. So in general, there is, for SUN, there is n square, where n is the dimension, minus 1 traceless condition, different matrices, and they're called bases. And it's now the only idea that you have to differentiate between finite groups and continuous groups is that for finite groups, you look at the algebra, multiplication table of the elements. But it turns out that for continuous group, you have to look at, composition laws of the generators. Because remember, the group is obtained by applying the operation, but now you have to figure out what it means in terms of generators when you apply the group several times. So that's the one big difference between the finite groups, permutation groups, cyclic, etc., the hedral groups, whatever you need to do in the practice, and continuous groups. You have to up your ante and you have to go up to the exponent, and that's why I started the whole course teaching you matrix functions, that you can actually make sense of matrix that can be written as a function of a matrix. So any unitary group can be written as e to the I, any unitary operation, matrix operation, where I have some finite number of parameters. Now, these matrices in exponent, there is a finite number of them. That's called now order of the continuous group. Order of the finite group was the number of elements in a group, but order of continuous group, you count the generators. For unitary groups, they're very nice matrices. They're Hermitian. And basically, Hermitian is a generalization of real number for matrices. It's a nice thing. And they have real parameters, which are compact because there is an I in front. So there is the same finite number of compact parameters. And, for SR3, you know it. You're on planet Earth, and you have to specify, where am I on which meridian, which parallel, and which way I'm looking. You have to specify 3 of these numbers. And in general, you have to specify n square because these are matrices of that size, but they satisfy, they're constructed for Hermitian matrices, and Hermitian matrices are glorified real matrices which have n square minus 1 components, n because n by n matrices, n square minus 1 because they're traceless. And what do you get? It used to be infinite number of group elements. Now, this is, I call it U because we're specializing to unitary matrices. Why do we specialize? Because they describe everything we have learned so far and much of what needs to be learned in group theory, in physics and engineering. Because unitary group is mother of all groups. On the left-hand side, I have a group product. And it's very nice to think in terms of explicit matrices. So matrix representation, that's what these guys are. I have closure. If I multiply 2 of these guys, I get another element of the group. And the way I define them, if they were finite, I define them by saying there is a multiplication table, and I take my n elements, multiply them by their inverses. I get e's on diagonal, and I get, some other elements here. I fill it out, and all realizations of symmetry which have the same multiplication table isomorphic to each other, they're the same finite subgroup on an abstract level. Now that we have gone up to exponents, we have to, adapt a little bit. And the main thing that happens is here we had a group product, but that'll be replaced by a commutator. And that was a big discovery of Sophus Lee. It says that when I look at these generators, I have to make sure that if I compose them in one order, multiply them as matrices, and then I compose them in the other order and subtract the two. So that's a difference that measures how non-abelian group is, because it's the difference that measures how generators of the group commute when I multiply two group elements. This still has to be a unitary group, which means that it has to be expressed in terms of some of these generators. And that constructs a table which is not now a multiplication table, so that's called structure constants. Two represent two totally different subgroups of unitary group, have the same structure constant, so you don't list product of two together third, but you list a so-called commutator product or Lie product of two together third one. If these numbers all agree, then that's the same group on the abstract level. And this multiplication table now is not called a group multiplication table, it's called Lie algebra. And, roughly speaking, difference between group and algebra is the group only has a product defined. But to make sense of algebra, you have to start adding things. So you have to add both multiplication and addition. And that gives you an algebra, has a little bit more of a structure. We have gotten to this point that, in terms of algebra, we have found out that every group that we care about is subgroup of UN, and UN can be described by finite number of generators by using the trick of writing something in exponential form. Now, how does this really work? It's still lots of stuff. So here is the main idea of how we think about Lie groups. I'm sorry, I used the word. So theory of this continuous group was developed by Sophus Lie, and brilliant and very suffering Norwegian mathematician. So, you'll see that name often, Lie, just a Norwegian family name. And here's what he understood. We're trying to describe something that has a form e to the I, phi I. And often, I will use a convention that if index repeated means it's summed over, so I don't have to write sums all the time. And, we are now trying to describe what it really does. I told you it's Hermitian matrices, I can parameterize it, but what does the stuff really do? Now, the main clue is that, and main intuition comes from thinking, I think, about planet Earth or perfect spheres, and then generalizing that from you start on a circle, but then you go on a sphere. And the main idea is that whenever there's this I here, we know that that will cause oscillation which means that there'll be finite ranges of this parameter. So that's what makes parameter compact. And now the idea is, what is this parameter? Like, for example, what is it when everybody is zero? So if I take phi I, phi 2, phi n of them, whatever the number is parameter, set them all equal to zero. Well, we know what it is. That's one. Set everybody zero, that's one. So we know that every group element has a one in it and then something else happens. Now, if you're on a perfect sphere, you can decide that your North Pole is here. So that a group element on this parameter space that corresponds to origin is here. But, if you're a Russian and you already invented this whole thing a long time ago, it happens that origin is not in Dallas, Texas, but it's in Moscow. So you develop your theory here, but Lobachevsky develops his theory there. And morally, they should be the same because it's a perfect sphere. So who cares what you choose as an origin? And we even have a word for it. We know that there is a conjugacy operation. I can take Lobachevsky, I can transport him by Aeroflot to Dallas, Texas. He can do his thing there and I can transport him back. And this is a perfectly well-defined group operation. I apply group element G, I do my thing, and then I do the inverse, and that's called conjugacy. So everybody is equivalent. And, if he finds his rules of how to think, let's say, about alpha 2, and he finds a basis, he has to find the same basis. This is unique. So these generators should be same for everybody, but what will differ is, he'll have different values of these FIs because he's in a different coordinate system. So there's some equivalence going on. And what that enables me to do is, both Lobachevsky and, Governor Abbott or somebody, we can both explore the neighborhood of this plane, which is, we have seen this lots of time. We can look at the tangent space here. And if you understand how things work in my neighborhood, it'll apply to every other neighborhood. And then I'll be able to piece my neighborhood to next one. I'll be able to produce global transformations. Sorry, I'm running over a little bit, but leave if you have other things to do. And what's a neighborhood? I'll take these phi's to be very small, called delta phi's. And then when I expand the series, as a Taylor series, I'll keep only one or two terms in these angles to describe the neighborhood which is near identity. And then I'm allowed to do this because all neighborhood are equivalent. They look the same because I'm on a perfect sphere. And, the same usual thing. The reason why I'm allowed to use Newton laws here and in Moscow is because they're equivalent up to rotations and translations. And same thing in translation is time. So this is our guiding principle. That if I understand any neighborhood, I understand all neighborhoods. So that's why people study neighborhood of identity to understand. That's what Lee did, to understand Lie groups. So let's, work out one example that you know about these things. Let's look at the simple group S of 2, which is so simple that in complex numbers it's U1. It's just multiplication by complex number. Nothing can be simpler. But let's think of it as real one. Then generator, which now I call R rather than U, parameterized by only one angle that's available, is, this is a group element, but I write it as e to the I theta parameter. There's only one. And then there is only one matrix here, which turns out to be one of the matrices we wrote before, but only one of them. There were three of them for SU2. Now this I can expand in the series, and I use the fact that if I call the Hermitian generator minus I0, 0, I use the fact that when I square it, it's 2 by 2 matrix. When I multiply it with itself, I get identity. Yeah, obvious. So that means that this infinite sum, Taylor series, n equals 0, I phi to the kth power over k factorial tk, the generator, this matrix, splits in only two matrices, either this one or that one, because every power is either odd powers are proportional to this, even powers are proportional to identity. And then you look at it and you realize this is actually just summing sines and cosines. So the diagonal part, every second power gives you cosine series. The off-diagonal part gives you sines. And you find out explicitly that this generator produces every possible rotation called special orthogonal, because it turns out that if you are working in neighborhood identity, the determinant is essentially determinant of identity. So there's no way to produce elements by continuous little steps, which are inversions of coordinates, which are humongous changes. That's what the orthogonal group allows, but special orthogonal doesn't. So here it is, an example of how you describe the simplest group. And, all abelian groups look like this, but we'll have to learn how to do non-abelian groups. To do that, it's a very similar situation to what we used to do when we went from cyclic rotation to flipping a triangle. SU2 or SO3 is the first group in which you have non-abelian stuff. And that's all. If you understand this, you understand almost everything, and that we'll do next week.